All right, guys, our fourth lesson's here. We're going to look at the properties of the limits that we've been learning about. Okay, so this first one here, our bell work. Obviously, if you haven't done it, pause the video, go give it a try. And if you have done it, then let's see if you did it correctly, all right? And we'll take a look at it here together. All right, so when we've got something like this, I mean, if you remember the binomial expansion, by all means, but I have a feeling most of you don't. So instead, what we're going to do is we're going to think of that as being 2 plus x squared times 2 plus x, rather than 2 plus x cubed. All right, and so we're going to rewrite this as the limit as x approaches 0 of, I'm going to do that 2 plus x quick here, because you guys are experts at factoring at this point. So it's going to be 4 plus 4x plus x squared, and then still times 2 plus x over x and minus 8. All right, so we're going to need to do that again. So the limit as x approaches 0. Now we've got to do the more complicated one, where we're going to take that 2 and multiply it into everything, and then multiply this x into everything. All right, so that's going to be 2 times 4 is 8, plus 2 times 4x is 8x, plus 2 times x squared is plus 2x squared. Now I'm going to multiply that x through everything. So plus 4x squared plus x cubed minus 8 at the end. And that whole thing is still going to be over x. So then what I can do is start to simplify this a little bit. You can see that the 8 and negative 8 cancel. And then I can put my x and x squareds together. And so I'm going to get the limit as x approaches 0. Let's put the x, let's do it in descending order. So x cubed plus 6x squared plus 12x. And it's still over x. And now you can see that now that x is a part of everything, which I'll show again here. Okay, I can pull out that common factor of x. I do not expect you to normally do this, but I'm doing it just to kind of refresh your memories on how this actually works. So because that x was in everything in the numerator, I can now cross it out like so, which just leaves me with the limit as x approaches 0 of that polynomial function. And now I can plug in my value. So I'm going to get 0 squared plus 6 times 0 plus 12, which obviously these go away, and I'm left with just 12. All right, next one was a little bit easier here, because when I plug in 3 for this, there is no problem. It's not going to, we're not going to create problems like we did up here, or when I plugged in the 0, I ended up getting 0 on the bottom. Here, I can't make this undefined, so instead I'm going to just plug it in. And so it's e to the power of 3 times the cosine of 3 pi over 3. Obviously, those 3's can simplify. And then I'm left with e3 cos pi. And hopefully you're familiar enough with the unit circle to know that this is negative 1. Therefore, it's simply going to be negative e cubed. All right, let's take a look now at the properties of limits. So when we've got these, the limit of f of x as x approaches a, we're going to write it as L. And for g of x, we're going to write it as m. Now, this is just so that we can understand these. I will also rewrite it in terms of limits, just so that you can see exactly what's going on. So if I have the limit of f of x plus g of x as x approaches a, that is the same thing as the limit as x approaches a of f of x plus the limit as x approaches a of g of x. So in other words, what that'll be equal to is L plus m, right? Because we already said this was equal to L, and the gx one is equal to m. Now, it works very much the same way when we're subtracting them. This is going to just be the limit as x approaches a of f of x minus the limit as x approaches a of g of x, or L minus m, once we actually take those limits. Now, when we end up with them divided, it's, again, exactly the same idea. So it's going to be the limit as x approaches a of f of x divided by the limit as x approaches a of g of x, which, since that is L and m, it would simply give us L divided by m. Now, if we multiply them, again, it's going to be the same thing. So this is quite literally the limit as x approaches a of f of x. And I'm going to use nice big parentheses or brackets here to kind of show this, times the limit as x approaches a of g of x, or L times m. Now, if I have c, some constant here, the c isn't affected by the limit. So it's the same as just saying c times the limit as x approaches a of f of x, which would ultimately just be c times our limit. And somewhat similarly here, if I've got all of that to the power of p, this is exactly the same as just saying the limit as x approaches a of f of x, all to the power of p. And if I take the limit of a constant, it doesn't really matter what I'm approaching. It's a constant. It's always the same thing. So it's just going to be c. All right, let's take a look and see if we can now apply these into some actual piecewise functions here. So for each of the following limits, apply the properties of limits. If it does not exist, the limit that is, then state why. So the limit as f of x plus g of x as x approaches 2 from the left. So the first part we got to do is just that f of x portion there. And if we look at that, as we approach 2 from the left, we're getting 3. And g of x, as we approach 2 from the left, we're getting 1. So in other words, this is simply going to be 3 plus 1, or 4. Now this one, if we've got that constant in front, remember that constant doesn't matter, so it's going to be 2 times whatever the limit of f of x as x approaches negative 1 is. As we look at negative 1, from both sides here, we're approaching negative 6. And then same thing here, the 3 is just going to be multiplied by whatever g of x is as we approach negative 1. And in both cases here, we're approaching negative 1. So ultimately we get 2 times negative 6, which is negative 12, minus 3 times negative 1, which is really plus 3, or negative 9. Why? Because it's a negative times a negative. Next one, we're going to approach negative 3 for f of x. As I approach negative 3, from both sides here, I get negative 2. And then I'm going to subtract g of x as I approach negative 3. Negative 3 is that asymptote, and since I approach two different things, positive infinity and negative infinity, it doesn't exist. Now, as soon as one of them doesn't exist, we just say the whole thing does not exist. Okay, we can't have just part of it there. All right, next up here, so this is going to be negative 2 times whatever the limit of f of x as it approaches 6 is, divided by whatever the limit of as x approaches 6 of g of x. So let's go find those. As we approach 6 here, in both cases, we're getting negative 4 for f of x. And for g of x, as we approach 6, in both cases, we're getting positive 6 here. So we're going to end up with, what is that, 8 over 6, or 4/3 when we simplify it. Here, again, this 2 is just a constant that's going to be up front, so it's literally going to be 2 times whatever the limit as x approaches 4 of f of x is, times the limit of whatever x approaching 4 of g of x is. So for f of x, as we approach 4, we're getting negative 3 there. As we approach 4 on g of x, so approaching 4 right here, from both sides, we are getting 4. Putting that all together, we're going to get negative 6 times 4 is negative 24. One last one over here. So we're going to take f of x as x approaches negative 2 and then square it. So as we approach negative 2, which is right here, from both the left and right, we're getting to negative 5. So it does exist, it's negative 5. Careful with the parentheses need to be around everything as we square this, because that makes it positive 25, not negative 25. Now, in this next one, you should start to recognize this because I made you do this in our review unit, right? This is extremely important, you guys. You need to know this because this is what's going to end up becoming a very key component of our next unit when we start doing derivatives. So it's very, very important that you understand it. So in this case, we're going to do the limit as h approaches 0, and we're going to plug in x plus h everywhere there's an x here. So that's 2 times x plus h squared minus 3 times x plus h plus 4. Then I need to subtract the entire function. This is where a lot of you guys forget to distribute through the negative. So minus 2x squared minus negative 3x is plus 3x minus 4. Okay? And then, of course, the whole thing is over h. So now what I need to do is I need to expand these out. So the limit as h approaches 0 of, I'm going to do this all at once because we're experts, right? X squared plus 2xh plus h squared. So it's going to be 2x squared plus 4xh plus 2h squared. Do the same thing here, minus 3x minus 3h plus 4 minus 2x squared plus 3x minus 4. A lot of stuff there, but you're going to see that now a whole bunch of it's going to start canceling out. 2x squared cancels with negative 2x squared. Negative 3x cancels with positive 3x. 4 cancels with negative 4. And you'll see that the only things left here are the ones that have the h term in it. So now the limit as h approaches 0 of 4xh plus 2h squared minus 3h all over h. And I told you before, I would not necessarily make you pull that h out each time to show that it's a common factor, but remember, I can only do this if it's in every term. So effectively what I'm doing, and I will show it one more time here, is that there's an h that comes out, and I'm left with 4x plus 2h minus 3, all multiplied by h over h, which is what allows me to get rid of that problem where I'm no longer dividing by 0. So now I can just plug in my 0 for h, and I'm left with 4x minus 3. Like I said, this is going to be super important because this here has significant in our next unit and really everything we're going to do in calculus. So make sure that you're comfortable with that, and let's look at the next ones here. So now what we're going to do is we're going to look at these limits of exponential functions, okay? This is not going to be a huge part of what we cover, but we are still going to cover it, and so I want you guys to just be, I guess, careful. We're going to really analyze the exponentials that we've done before. So in our exponentials from pre-calc, we know that they're in the form of like ab to the power of x, where b is our growth rate. And we get two different possibilities. So we can have them grow, where we get one of these two shapes, or we can have decay, where we get one of these two shapes, okay? If it is growing like this, then that means that our b value is positive, or, sorry, it's greater than 1, or it is less than 1, and a is negative, which would cause it to flip into this one. Or b could be a fraction, which would give us this one, or it could be greater than 1, and a is negative, making it into this one here, okay? So those are our options. If I'm looking at this one, my b value, or my growth rate, is a fraction less than 1, okay? And the number in front is not negative, it's positive 1. Even though it's not written there, it is positive 1. All right, let's take a look at what these are now. The limit as x approaches negative infinity. So as we go to the extreme left, this thing keeps going up. Therefore, it's going to go to positive infinity. As we go to the extreme right here, we're approaching that asymptote, and so we're going to get to negative 2. Now, likewise, if I look at this one here, okay, this time I've got a growth, because you can see here r is greater than 1, and a is also positive, meaning it's growing like this, okay? As we go to the extreme left, now we're approaching that asymptote, that negative 2. And as I go to the extreme right, I'm going up into infinity. All right, we got two more examples here. Here we've got what should be a decay, which would look like this, but see how a is negative and it flipped it upside down, so it actually became a growth of sorts. But what we're looking at is that end behavior. If I go to the extreme left here, I am going to plunge down into negative infinity. And if I go to the extreme right, I'm going to approach that asymptote and get to, looks like negative 1 there. All right, now the other one here, oops, got rid of the equation. You can see once again, this one should have been a decay. Now this one's pretty confusing here because this one's got a negative a value, which would flip it this way, but it also has a negative b value, which means it flipped it to like this. If you don't fully understand those, oh my goodness, transformations, that's okay. We're not going to spend a lot of time on it, but it does definitely help us do these a little faster and understand what's going on. So in this case, we're just graphically looking at, if I go to the extreme left, what am I doing? I'm approaching 2. And if I go to the extreme right, it's plunging down here into negative infinity. So when we're looking at this, if we're looking at that end behavior, when we go to the extreme left or the extreme right, we've only got three cases. Either we go to negative infinity, we go to a number, which is a horizontal asymptote, or we go to positive infinity. There is no other option. So hopefully you guys that made some sense, and go give those practice problems a try.